projection of a vector on the one-dimensional subspace. Today we will see the projection in general subspaces. So in this we will look at the orthogonal projections of the vectors x r to the power n on lower dimensional subspace, which is a subset of the vector space whose dimension is n and the dimensional of the subspace is m that is greater than or equal to 1. That means the subspace can be generated from the m basic vectors b1 to bm is an orthogonal basis of u, ordered basis of u, sorry. Any projection pi ux on this subspace U is necessarily an element of U. So it can be represented as the linear combinations of the basis vector b1 to bm. Because they are linearly independent, so we can write the pi ux as the summation of the linear combination of the basis vectors of b1 to bm, that is summation I equal to 1 to m lambda I bi, lambda 1 b1 plus lambda 2 b2 up to so on. Now, how can we find the pi ux? We will go to find the three things. How we will find the projection point, projection matrix, and the coordinates. So, steps to find the projections pi ux and the projection matrix p pi. So, first of all, finding the coordinates that are from lambda 1 to lambda m of the projections such that the linear combination is closest to x, as we have seen in the one dimension also. The distance is closest to the x. That means we know that the pi ux is the linear combinations of the lambda I and bi of basis vector, which can be represented as b into lambda, where b is the matrix of the basis vector whose dimensions is n cross m, in which n rows and m columns, and lambda is the vector of the matrix of the coordinates. So closest implies that the minimum distance that the vector connecting pi ux and x must be orthogonal. That means it should be the perpendicular distance. So we can say that it is the minimum one. So if the pi ux and x must be orthogonal, then their inner product should be 0. So the distance from the basis vectors b1 into x minus their inner product of b1 and x minus pi ux should be 0 up to bm x minus pi ux should be 0. So which is the Euclidean inner product, which can be write as the b1 transpose into x minus pi ux, that is equal to 0 up to bm transpose into x minus pi ux up to 0. And we also know that from the previous result that p pi ux is equal to b lambda. So we can put here b lambda here. So it is b lambda, b lambda, b lambda. We obtain a homogeneous system of linear equations. So that is one matrix of the b1 transpose to bm transpose, and the other one is x minus b lambda. Their product will be 0. This is the homogeneous linear equation system, which can also be written as b transpose into x minus b lambda is equal to 0, which is b transpose into b into lambda is equal to. This equation is known as the normal equation, since b1 to bm are bases of u and therefore linearly independent. So b transpose into b is r cross m cross n is irregular and can be inverted, and we can find the lambda from this normal equation, that is the b transpose b inverse. It will comes here as inverse of the b transpose b, and this will remain same. So this is the result of the coordinate lambda. So the matrix, this is known as the pseudo inverse matrix of b. So in the result we will find the lambda using this property of orthogonality. After that, the next step is to find the projection point, that is the pi ux, which is on the subspace U. So as we know that pi ux is b lambda, and we have also from the previous result the value of lambda we will put here, and we will get the result of pi ux. In this section we will discover the results and we will do the questions on these results. So use this lambda of the previous result and we will get the pi ux. This is the projection of x vector x on the subspace U. Finding the projection matrix p pi, the third one step. As we know from the one dimension also that p pi into x, that is equal to pi ux. So p pi is the projection matrix, And we, from the previous result, we know the pi ux also. Here is the result formula of pi ux, and we can put here, and we will also get the result of projection matrix. So all the three things we can find for the general subspaces of m dimensionals. So let us take an example on this, how we can find these, the projection matrix, the coordinate lambda, and the projection point pi ux. So for a subspace U, that is the span of these two vectors. If the vector U, if the subspace is span of these two vectors, then these two vectors becomes the basis of this U. And let us assume a vector x, for which we are going to find the projection of this x. So finding the coordinates lambda of x in terms of U, projection point pi ux, and the projection matrix, all the three things we are going to find. So first of all, the basis vectors of U we can write in a matrix format, that will become the B111 012 from the B1 and B2. This is B1 and this is B2. So this is the matrix of the basis vectors. We can compute that the matrix B transpose into B and the B transpose into X, as because we have B also. And
Yeah, so this is basically the rectangular matrix,
yes sir,
right? So pseudo inverse is essentially the generalized inverse.
yes sir.
So
So
we cannot find the determinant of, as we discussed earlier, we cannot find its determinant of B,
yes, yes sir,
right? Because it is not a square matrix. So
yes
we
sir,
are finding B transpose B, which is a square matrix.
which is square matrix.
So
Yes sir,
its inverse we can find,
yes sir, its inverse we can find, pseudo inverse. Yes sir,
right? So this is a good example. Okay,
yes sir,
continue. Continue.
yes sir. And we will find B transpose B, that will comes out to be square matrix, and B transpose into X. Now we will going to solve this normal equation in order to find the coordinate lambda, as we have discussed previously. The to finding the, we have to solve this normal equation in order to find the coordinate lambda. And we also know that B transpose B inverse is called the pseudo inverse also. So we can put the value of B transpose B and all the things, we will get the matrix of our coordinates lambda. So this is the first thing we what we have solved about the coordinate lambda. Now the next point is the to find the projection of vector x on the subspace U. So pi ux, that is equals to b lambda, we also know that. And what we have, b and lambda, after multiplying these two things, b matrix into lambda matrix, that we have got in this result, we will get the projection. This is the
Yeah.
projection
What
point.
is the last equation?
What sir? The last result.
Uh, yeah,
This
this
is
B transpose B lambda, that equation.
b transpose b lambda. That is the result for the pi ux, that is b lambda. We have seen here also the pi ux, that is the b lambda. So we have b and lambda. By multiplying these two things, product of these two matrix, we will get the pi ux in
Right.
this.
So how that equation is related to this equation? B transpose B lambda is B transpose
So we are using the formula of pi ux also.
pi x. Yeah. And
Yes,
what is pi x?
pi ux
It is
is
B
the,
transpose B transpose B inverse B transpose X.
yes sir, b transpose b inverse b transpose x. Yes sir,
Yeah. So go
this
to
is the,
that computation, that lambda you found, no? That,
yes sir, lambda we have found already.
go to that equation, that
Yes sir,
computation.
yes sir,
So in this, yeah, this equation.
yes sir, this is the
So
normal.
here, how this equation came? That is my question.
This equation, b
Yes.
transpose b lambda is equal to b transpose into x. So
Yeah.
this was the 1 minute, 1 minute. I have to again see the all the things. So from this one, after solving these, we know that this is the linear combination. After that, which can be written as b lambda pi ux. After that, after solving this, we get this system of the linear equations. We
So
got this. Yes, sir.
go to the last equation, last page.
Last page.
Yeah. So see how this equation came, that we want to understand.
This equation.
Yes.
Yes, sir. This equation comes from the linear equation system of these two. Yes, sir. This equation comes from the property of orthogonality. After applying this property, we obtain this linear homogeneous system of B1 transpose to Bm into x minus B lambda, which can be written as this
Okay,
B
so that
transpose into x minus B lambda.
that came. So this is coming as a system and how that system came.
This system came.
Yeah.
So this system comes when we solving these equations of after applying the property of orthogonality. These equations.
Yeah, so go to the last page.
Yes, sir. Yes, sir.
No, that equation last page.
Page number can you tell?
नहीं नहीं, अभी जो दिखा रहे थे ना वो सिस्टम ऑफ लीनियर इक्वेशन वाला,
यस सर, ओके ओके।
उसके जो आगे का कंप्यूटेशन,
अच्छा, आगे का ये वाला कंप्यूटेशन सर है।
इससे आगे ये सब कहाँ से आ रहा है, हाउ दिस इक्वेशंस आर कमिंग?
Yes, sir. These equations are coming from sir this property of orthogonal to the basis vectors
मिनिमम
because
डिस्टेंस यू आर फाइंडिंग, ओके।
yes sir,
सो
orthogonal. I have discussed this about the orthogonal. Sir, my internet is coming or not?
या आई कैन सी द स्लाइड्स,
Okay, sir.
सी द पीडीएफ।
Okay, sir. I thought that the previous thing I have missed and I am directly
Oh no,
solving the
that
example.
I but you've taken very speedily. So
Okay.
I was just looking. So basically, you are finding the minimum distance.
Yes, sir. Minimum distance.
That's
There
why
was.
you are using the projection.
Yes,
Oh,
sir. Yes, sir. That was the concept behind this.
okay, okay. So
Okay, sir.
continue.
Okay, sir. I am continuing. I will try to slow my speed right now. Okay. So one thing we have discussed about the lambda also. Here the lambda we have find. Now we know that the pi ux is b lambda and we have b vector, and in the previous one we have find the lambda. After product of these two matrix we will get the projection point. After the projection point, the corresponding projection error. One more thing in this including in the book, that is the projection error is the norm of the difference between the vectors between the original vector and the projection vector onto the subspace U. So norm is the difference between the projection vector and the normal vector. We will take the norm of these two and we will get the projection error from this. No more discussion about this on the topic, but only this line about the projection error was given in the book. And lastly, the projection matrix, we have derived the formula of projection matrix above, that is the B transpose B inverse, that is the pseudo inverse into B transpose. So we have all the things and we will put the value and find the projection matrix. So this was the example
So
of
what is the property of the projection?
projection.
Yeah. So why it is called projection? So did you study projection in the linear transformation?
Sir, I have studied the projection in the general subspace of vector U,
Vector
vector
space.
space. Yes, sir.
Okay. So usually the linear transformation is a projection if it is idempotent,
Yes, sir. Yes, sir.
right? So go to the last computation you were discussing, that projection you found.
About the projection matrix.
Yeah, yeah. So
Yes, sir.
here
This
you
was.
see this
Yes,
projection formula is B transpose B inverse B transpose.
yes, sir.
So when you apply two times, it will be B transpose B inverse B transpose multiplied to B transpose B inverse B transpose. So in between there will be B transpose B, that will cancel with one B transpose B inverse.
Yes, sir.
So you will get the
Understood.
same thing, right? So basically P pi composition P pi is P pi.
So P pi is will be P pi composition of it.
Yeah. So it is a that is idempotent. Therefore it is projection. So any
Okay.
transformation T is projection if it T square is T.
Yes, sir, yes. That thing I have missed, I think so, in this concept about the idea important.
Yeah. So that,
Yes,
okay. So this you found projection.
yes, sir. I will study more about this the
Yeah.
projection
But
matrix
projection
in the.
usually we find, so in this example we found the projection which is kind of a general projection, because the projection we are finding using pseudo inverse, right?
Yes, sir. Yes.
So that way this procedure is So this is essentially the minimum distance, means it is that least square method it is known as, so for computation of error.
Yes, sir. Yes, sir.
But
Computation of.
yeah, so this is in that way it is general method, because we are using pseudo inverse instead of the usual inverse of the square matrix.
Yes, sir. We are. This is the, sir, I think pseudo inverse
Pseudo
matrix.
inverse, yes. Yeah, so you continue, please.
Okay, sir. So this was the whole topic behind the general subspace projection on the general subspace. Now the next topic is the Gram-Schmidt orthogonalization. It allows us to constructively transform any basis vector, that is the b1 to bn of an n-dimensional vector space. So it will transform this basis vector to the orthogonal basis u1 to un, that is the vector space V. सो यही यही बताता है कि b1 to bn के किसी भी बेसिस वेक्टर को ऑर्थोगोनल बेसिस वेक्टर के अंदर ट्रांसफॉर्म कर देता है ग्राम स्किमिड ऑर्थोगोनलाइजेशन. इसकी कुछ एल्गोरिदम्स है. अच्छा, इसकी प्रॉपर्टी, द प्रॉपर्टी ऑफ दिस इज द स्पैन ऑफ b1 to bn is same as the span of the orthogonal basis vector, that is u1 to un. That means this span will generate the vector space, the same vector space is generated by the from the b1 to bn basis vector. That is the main thing of the Gram-Schmidt orthogonalization. Now we will see how Gram-Schmidt orthogonalization actually works, how to find the orthogonal basis from the normal basis. So method, that is the iteratively construction of an orthogonal basis u1 to un. So how we will construct u1 to un from any basis b1 to bn of a vector space V, as the u1 is equal to the b1, and for any uk where k is from 2 to n, for k is equal to 1, u1 is equal to b1, and for any uk we will subtract the projection of vector bk onto the subspace that is spanned by the vector u1 to uk minus 1 from the vector bk, from the basis vector bk. This we will get the uk, any orthogonal basis vector uk. This is the main algorithm to find the any basis vector uk. So that means what I have learned from here, that the kth basis vector bk is projected onto the subspace spanned by the first k minus 1 orthogonal vectors. These are the first k minus 1, u1 to uk minus 1. These are the first k minus 1 orthogonal vectors, and the span of these vectors, we will project our bk vector on the subspace of the span of these first k minus 1 orthogonal vectors, and subtract this projection from the basis vector bk. We will get the orthogonal vector uk. This is the main algorithm behind this. So first k minus 1, that is the u1 to uk minus 1, this projection is subtracted from the bk and yields a vector uk that is orthogonal to the k minus 1 dimensional subspaces that are spanned by u1 to uk minus 1. This was the whole concept behind the Gram-Schmidt orthogonalization. And if we repeated this procedure for all the basis vectors b1 to bn, then we can yield our all the orthogonal basis, that is u1 to un of the vector space V. If we repeated this process of uk for k is equal to 2, k is equal to 3, and up to k is equal to n, we are able to generate all the u1 to un that are the orthogonal basis for a basis vector b1 to bn. So this is the Gram-Schmidt orthogonalization. Let us consider a simple example on this to understand the whole topic, how these are working and whole concept. So let us consider an example on the Gram-Schmidt orthogonalization. The example, in this example, first of all, we will see the three scenarios here. The first scenario, in the two basis vectors, these are the original basis vectors, non-orthogonal basis vectors, b1 and b2. These two are the original basis vector. After this, what have happened, first new basis vector u1 is equal to b1 and the projection of b2 on the subspace of the spanned by the u1. What it is, we have generated one orthogonal vector, that is the u1, and what we have seen, u1 must be equal to b1. From here u1 should be equal to b1. So we have generated u1, and the projection of this vector b2, this is the vector b2 and this is the projection, and the projection of b2 is on the, what we have seen, it is spanned by the orthogonal vector u1, that is the first k minus 1, that property we have applied here. The projection is on the spanned by the first k minus 1 orthogonal vectors. So now we have generated first orthogonal vector u1. After this I want to generate the second orthogonal vector u2 from this. So this is the u1 and this is the u2. How we can generate u2? We can put k is equal to 2 in this equation. In this equation we can put k is equal to 2. We get u2 as b2 minus span projection of the b2 on the span u1. So what was the b2 vector? This is the b2 vector. इसमें से we can minus, that means this is the second vector we are subtracting from the b2. This is the negative direction of this vector. This is the positive direction, this is the negative, because this is the negative projection of the spanned by the u1. This is the negative projection and we get our resultant u2 here. This is our second orthogonal vector u2. So in the third case what we have generated, that is the second orthogonal vector u2. And in the same phase, if we are repeating this process of this uk for k is equal to 3, k is equal to 4, up to k is equal to n, we can generate the basis of the orthogonal vector b1 to bn. So in this, what we have given in this example, a basis vector b1 and b2, where b1 is given and also b2 is given. What we have, using Gram-Schmidt method, we construct an orthogonal basis. What we want to construct, that is the orthogonal basis of u1 u2, as we know that u1 is equal to b1. So first orthogonal vector u1 we found from the b1. Second, by putting k is equal to 2 in the above equation, u2 is equal to b2 minus the projection of b2 in the span of the u1 vector. So b2 minus the pi projection formula we can apply from here, that is u1 into u1 transpose upon norm of u1 ka square into b2. We can apply these things, and what we have, u1 we have b1, so we can put the value of u1 here, u1 transpose upon norm of u1 square into b2, and we have b2 also, so we can found the u2 also. So from this, from the above equation of uk, we can find the u1 and u2 both. So this was the whole concept of the Gram-Schmidt orthogonalization. We can transform a basis vector into the orthogonal basis vector. So this was the end of the topic regarding the grams. One more topic remains. I will continue in the next presentation of rotations in this analytic geometry.
Okay.